Hello everyone, this is Vasant, a nine-pointer at IIT Bombay from the Department of Civil Engineering. Today we are going to discuss about elastic constants. So elastic constants, first we need to know what are elastic constants. Elastic constants are E, G, K and nu. We already know what is E, that is modulus of elasticity, right? We already know what is G, modulus of rigidity. We already know what is K, that is bulk modulus. Mu is Poisson's ratio. These are elastic properties, right? These depend on material, so these are material properties. Okay. So, but why we call it as constants? Do they really constant for a material? No. But for homogeneous and isotropic material, these have single value throughout the material, right? So I also said that in solid mechanics, we generally deal with homogeneous and isotropic materials. So as in homogeneous and isotropic materials, we have single values throughout the element. So we can say these are elastic constants, at least for homogeneous and isotropic materials. Okay. So do we have relationship between uh, these four elastic properties? Yes, there is relationship between among these four elastic properties. Actually, there are two relationships, two independent relationships. One is G is equals to 2 into G is equals to E by 2 into 1 plus mu. That can also be written as E is equals to 2G into 1 plus mu. And one is E is equals to 3K into 1 minus 2 mu. Okay. Then what is relation between E, comma, K, comma, G? This is dependent one. So from these two things, we can write mu is equals to E by 2G minus 1, right? So we can substitute over second equation 3k 1 minus 2 of E by 2G minus 1, right? So E is equals to 3k into 2 plus 3 minus E by G. So that will give us E is equals to 9k minus 3ke divided by G. So E of 1 plus 3k divided by G is equals to 9k. So this will give us E is equals to 9 kg divided by 3k plus G. Okay. So this is relationship between E comma K comma G. So these are two independent relationships. So yes. So what is the range of Poisson's ratio? See, we already discussed what is the value of Poisson's ratio. That is minus 1 less than or is equals to mu less than or is equals to 0.5, right? Minus 1 less than or is equals to mu less than 0 will be for oxidic materials. Right? And 0 less than or is equals to mu less than or is equals to 0.5. That will be for general materials, for example, metals, etc., which we generally use in civil engineering. Okay. How these values were taken? See, E is equals to 2G into 1 plus mu and E is equals to 3K into 1 minus 2 mu. Okay. So we already know that E comma G comma K are always positive, their values, right? Yes, nu can be positive or negative. So see, from this this is positive, this is positive, then automatically this should be positive. So from this we get that 1 plus nu should be greater than or is equals to 0. From that nu should be greater than or is equals to minus 1. Right? Now from this one we already know that E is positive, K is positive, so this should also be positive. So 1 minus 2 nu should be greater than or equals to 0. Then 1 should be greater than or equals to 2 nu. That gives 2 nu greater than or equals to 1. Nu, sorry, less than or equals to 1. Nu less than or equals to 0.5. So combining these two, we get minus 1 less than or equals to nu less than or equals to 0.5. Okay. So this is about range of Poisson's ratio. Now let us go to volumetric strain. See, we generally in this chapter we generally discussed linear strain, right? Means change in length dimension. Single length dimension epsilon will be equals to change in length divided by original length. But there can be areal strain also. That is epsilon A is equals to change in area divided by area. Similarly, there is volumetric strain denoted by EV. So that EV will be is equals to change in volume divided by original volume, right? So let us prove the value of volumetric strain. So let us take a cube, one dimension, one unit cube, okay, one unit cube. So in x direction, the net strain is epsilon x. In y direction, the net strain is in z direction, the net strain is epsilon z. In y direction, the net strain is epsilon y. Then new volume will be 1 plus epsilon x, that is length in new length in x direction into 1 plus epsilon y new length in y direction into 1 plus epsilon z new length in z direction. This is final volume minus what is initial volume, that is 1 divided by 1 is the original volume. That will be delta V by V, right? So that is equals to 1 plus epsilon x plus epsilon y plus epsilon z plus epsilon x epsilon y plus epsilon y epsilon z, right, plus epsilon zx plus epsilon x epsilon y epsilon z minus 1 divided by 1. This one gets cancelled, right? So see, generally in civil engineering structures which we consider, epsilon x epsilon y epsilon z are small. Okay, so we can neglect epsilon x into epsilon y into epsilon z, epsilon z into epsilon x into epsilon y into epsilon z. These can be neglected to 0, right? Assuming it to be 0. So this one cancel. We get epsilon x plus epsilon y plus epsilon z. So delta V by V, that is volumetric strain, will be is equals to epsilon x plus epsilon y plus epsilon z. This is approximated one. The original value is this one. The original value includes this one also. So the original value will be greater than this value, greater than or is equals to this value, right? So this is about epsilon V. So now we also need to prove that for incompressible materials, the value of Poisson's ratio is 0.5. We already said in previous lecture. So if you observe in multi-axial loading, epsilon x plus epsilon y plus epsilon z in case of multi-axial loading is, if you add all the formulas which we derived in generalized Hooke's law section, you will get this one. Okay. So for this is equals to epsilon V for incompressible materials. epsilon v should be equals to 0, right? So 1 minus 2v into sigma x plus sigma y plus sigma z divided by E should be 0. See, there are two possibilities. One is 1 minus 2 nu is equals to 0, and there is sigma x plus sigma y plus sigma z is equals to 0. But what are incompressible materials? In incompressible materials, whatever may be the value of sigma x, sigma y, sigma z, the delta V should be 0, change in volume should be 0. So in one particular case of, in 2 to 3 particular case of loading, sigma x plus sigma y plus sigma z may be 0, but it is not always true, right? So the only possibility left over here is from this 1 minus 2 nu is equals to 0. From this we get nu is equals to half, that is nu is equals to 0.5. So for incompressible materials, the Poisson's ratio is 0.5, right? So this is about incompressible materials. And one more thing I want to say, whatever materials we use generally in civil engineering are incompressible materials, okay? In incompressible materials, the density remains generally constant. So that is the case of incompressible materials. So generally we use incompressible materials in civil engineering structures, okay? So with this, we end today's class. Thank you from ninepointer.